Okay, so today we will start with first of all we will start with what are known as affine hulls. Actually, this is a part of a big branch of mathematics called affine mapping, affine geometry, etc. Try it slightly bigger if it's not clear. Affine geometry and affine mapping. I am not sure if you have done it in mathematics. If you have not, okay, it's kind of very similar to your concept of geometric similarity I mentioned in the last class, but for the purpose of this class I will repeat it again. That is, what we have here is we have a ship, let us say a hull that is of some length, breadth and draft. We call x, y and z as usual, and now suppose I make a new hull such that its length is r x times length of the, let us call it the model is r x times length of the prototype, breadth of the model is r y times breadth of the prototype, and depth of the model is r z times the depth of the prototype. So, you are basically kind of changing the hull form into a different kind of shape. In this case, r x and r y and r z are non-dimensional numbers, which are the scales, very similar to our geometric scaling which I said. So, length is scaled by some factor, breadth is scaled, that is the meaning of this. Now, the ship from which you are making the transformation is called a parent hull, and the new shape that you are making is called as an affine hull. Now, of course, it is possible that r x is equal to r y equal to r z. It is a particular case of this mapping. Now, this process is called affine mapping. So, you are transforming from a ship to a model. So, that process is called an affine mapping, and the hull is called an affine hull. Now, the particular case when r x equals r y equal to r z is called as geometrical similarity. This I did talk about in the other class. We did problems relating to the shape of the vessel. There we mentioned that the shape of the vessel is always scaled by some factor. There is some factor r, which shows that r x equals r y equal to r z. Its every length direction is scaled in the same ratio. So, this is the concept of affine hulls. Now, we know that the initial volume of a vessel is given by, now suppose that the hull is transformed using this into a new hull okay. It is transformed using this similarity, this transformation. Therefore, the volume of the new hull will become okay, because these r x, r y, r z are all constants. So, they do not affect the differential. So, it is r x, r y, r z into dx, dy, dz. Therefore, del 1 is equal to r x, r y, r z into dx, dy, dz is equal to r x, r y, r z into del 0, which is our initial volume. Okay. The initial volume is del 0. So, this is your expression for the final displacement if you are doing a in this case it is not geometrical mapping because they are different. Let us call it affine mapping. In case of affine mapping, this will be the new displacement, and in case of geometrical similarity you get del 1 is equal to r cube del 0 directly from this. Now, you will see that when you do this kind of mapping, we are not doing the derivation, but it is very simple. If you you just need to substitute in the equations. we have the equations for LCB, LCF, etc. now and KB. Now we have the equations for LCB, LCF and LC and KB, we have already derived those. Now in the case of this affine mapping, the new LCB, LCB1 will become, you can do one thing, you can do this, that is you can, if you remember, LCB is always the distance taken along the x direction. Okay. So that you should be knowing firmly. So it is in the x direction, therefore you get the concept of Rx into LCB, it is not dependent upon Ry and Rz. And similarly with LCF, 1 will become Rx into LCF0. Okay. If LCB0, LCF0 are that of the big ship and KB0, and what do you think KB1 in that case will be? Rz into KB0. It is just like our intuition will tell you that a guess, it is a good guess would tell you that it is like this. So, and you can get this because you can just do this, that is LCB is equal to integral of x into del x d del, like what is your LCB? LCB is moment divided by volume. So, it is x into delta divided by delta. So, that is why that x becomes Rx into x, that is why that Rx term comes in the in your LCB term. Okay. So, you get LCB1 is equal to Rx, just like that KB and LCF. Longitudinal center of flotation and KB are scaled up in the same values, in the same ratio, and so we have delta 1 is equal to R cube delta 0. Now taking logarithm on both sides, you will get now if you differentiate both sides, because delta 0 is a constant, because delta 0 is your it does not depend upon. Now note that this differential you are doing with respect to R, that means the scale keeps changing. When the scale is changing, how is del changing as a result of that? That is what we are trying to do here. Therefore, delta 0 is a constant. So, this differential will become 0, differential of this will become 0. So, it just becomes this. So, what this says is that the percentage change of displacement volume, which you get from this, the percentage change is 3 times the percentage change of the ratio. Okay, the percentage change of volume, of course, it comes directly from this formula, you can see that, but I am just saying it, percentage change in volume is 3 times the percentage change in ratio. That is the ratio with which you are doing the affine mapping. So, this is, so with this we are finishing the chapter on hydrostatic curves. We have finished hydrostatic curves. Now we go to stability curves. So, I told you before that we have a couple of important things in this course. I told you that some of the most important ones, like point wise, if I had to write, the most important formula would be that for stability Gm should be greater than 0. That must be, I guess it would be the most important part of this course. Then the next important would be this stability curve that I am going to do next. Okay. So, this, what is most important is, of course, the theory behind that is also important, but it is finally that curve itself which I am going to draw sometime now. That curve itself is very, very important, because not only from for exam, for the course also it is important, but Viva everybody surely asks this question. This is every time, almost every student is asked at least one question related to this. So, for that, from that point of view, you should understand this, and for your interviews also they ask about this curve. It is known as stability curve or statical stability curve. Now, first we come to the, or they are called the curves of stability. curve of statical stability curve, these are the same things. Then we talk about, first let us see what is meant by a writing arm. We have done this in some related ways, but let us put it in the real definition. That is, okay, you have the cross section, you have a water line, then the ship heels to W1 L1 or W5 L5, then it is heeled by an angle phi. Now, your G is initially here and your B0 is here. Because of the heeling, B0 this shifts to here, B1, and from here I am drawing a vertical. This point becomes M, all this. Now, as you can see, there are two forces. I have already probably mentioned what is a writing arm. That is, you see there are two forces acting here. You have at G here in the final state. Let us consider the final state, that is the W1 L1 when the ship is heeled. Now, here you have the weight delta acting, the weight of the ship, that is acting at the center of gravity. Now, at B1, the center of buoyancy, there is a delta acting upwards. The weight of the again, weight is balanced, it is not moving up or down. So, that same force, that delta is acting upwards. Now, you can see there is a moment between these two. So, the perpendicular distance between this G and this line will give you, so delta into that perpendicular distance will give you the moment acting, right. So, again what I am trying to find here is the moment that is produced due to these two forces. There are two forces acting here. One is the weight of the ship, again the weight of the ship acting at a distance B upwards, that is a buoyancy force. So, weight of the ship and buoyancy force are acting here and here. So, this is causing a moment like this. Now, to get the moment, I have to multiply the force with the distance between them. So, this perpendicular distance between the two forces is what you call as a writing moment. This perpendicular distance is called as the writing moment. I mean writing arm, not moment, sorry. Writing moment is this, okay. This is delta into, this is a writing moment, and this is known as a writing arm. Arm always stands for distance. So, writing arm it is called, and this distance is G, and let us call that this is a 90 degrees angle, okay. So, that GZ is known as the writing arm, and these terms are fixed, do not change any of it. M always represents the metacenter, G is always the center of gravity, B is the center of buoyancy, like that Z is the point which indicates the writing arm. So, GZ always represents this distance, you cannot put Z for any other term, I mean any other point. So, GM, GZ, BM, KM, all those points notations are all fixed by everyone, nobody changes it. So, GZ is known as the writing arm. Now, if you just look at that figure, this figure, you will see that what is the writing moment? Writing moment is delta into GZ, okay. This is the writing moment, the force into the perpendicular distance between them. Now, GZ you can, I will use, okay, I will keep it here like this. And GZ from the figure you will see that GZ is equal to this is perpendicular distance again, okay. This distance is, let us call it as LK, and so you understand what is LK, right. It is the distance from the keel, the center of that point keel to this line. this vertical is drawn completely from B, from the new position of the center of buoyancy. That vertical is drawn, it hits the initial center line at M, the metacenter, which you know, and it hits the bottom at some point. So, this distance is Lk. Now, Gz is equal to Lk minus, this is K, Kg sin phi. This angle is phi. Which angle is phi? This one. This angle is phi, okay, or there is no space here, but I will mark it. This is phi. It's not at all clear in that. Should I draw it again? Anyway, I think you can see it, but probably they can see that this small angle between K M and this is phi, and Gz is equal to Lk minus Kg sin phi. This Lk, you call it now. Lk is a particular name given to it. It is known as the value of stability cross curves, or it is also known as lever arm of okay, all those names are actually Lk, we do not really use it. It is known as the lever arm of stability of form. I am not going to go too much into that, because Lk is not our main interest. Our interest is Gz, but just know that Lk is known as the value of stability cross curves. It is also known as the lever arm of stability of form, whereas this Kg sin, you see how it has become Lk minus Kg sin phi, right. That is, if you want, you can look at the figure again. That is this, let us see, Kg. Now, what we want is Gz, it is this distance, this is what we want, it is equal to this whole distance minus this much distance. So, this whole distance is Lk minus this distance. So, take this triangle K, G and this point. So, this angle will also be phi. So, Kg sin phi, all right. So, that is Lk is, you know. Now, similarly, looking at this figure, you can get the more important relation, that is the relation between Gz and Gm. You have the, actually I will just draw the triangle alone. You have M here, you have G below it, and you have, actually this angle is 90 degree, okay. This is Z. You have a curve like this is phi. Therefore, Gz is a Gm sin phi, right? Yes, Gm sin phi. Okay, this is the actually one of the very important relationships you have to remember, which you have to by heart. The relation between the writing arm and the metacentric height. Gz is equal to it is very simple if you draw the figure. So, in a way, if you can draw this figure, you can solve the whole problem. The whole problems related, as we, if you remember all the things that we have done so far, I have always drawn a cross section like this. I have always still healed it in some angle, and then it is just, you have to know a couple of things. One, you have to know the position of G's. Initial G, it will be in the initial center line, and G is not changing mostly because of this. Then there is always a healing, as a result of which some wedge goes there, something immersed here, wedge is opening up here or emerging out here, as a result of which the B is shifting. So, this figure you should be able to draw that concept. If you are able to draw this G, B0, B1, M, and this concept, that is, we have also mentioned this couple of times, that is B0 is going to B1, that transfer of B0. If you know this, you also know the positions of all these points. B0, which is 2 by 3 of this distance, this is again 2 by 3 of this distance, things like that. If you remember all those, it is just a, then of course, you have to know that Gm greater than phi. If you know these things, it is just a combination of these things. The problems will only be some kind of reordering of this, you just have to find the things. So, this figure you have to have in mind, and this concept, and when you can, if you can draw that figure, of course, you can easily derive this Gz is equal to Gm sin phi, provided you know that this angle concept, this angle is phi, if this angle is phi, similarly this angle will also be phi, the angle at which it is tilting. So, this concept you have to know, Gz is equal to Gm sin phi. Now, if you draw a figure between the displacement volume and the Lk, that is the what is it called, the lever arm, the lever arm of stability of form, it is called the lever arm of stability of form. So, Lk, so you will get a series of lines. Now, actually this Lk, if you look at this figure, this Lk will depend upon this angle through which it is healed. So, for different angles of heel you will have different values of Lk. Anyway, you will have different curves. These curves are known as cross curves of stability. Cross curves of stability, and just so that you know, this is not the important part, the important part is what comes next. Just know that this curve is called the cross curves of stability. Next one is more important, this is known as the statical stability curve. As I said before, this is the probably one of the most important things in the course. Now, the curve comes something like this. First of all, it is a curve between heel angle, which is phi, and between Gz, is it in meter. So, this is the writing arm. So, the statical stability curve is actually the curve between the heel angle and your writing arm. So, and it is actually the shape of this curve which is the most important, this shape. Okay. So, this shape is the most important thing in this curve, means that it is the fact that it increases to a value, maximum value, and then decreases. Note that if your Gz increases, what does it mean? Writing arm is increasing, means if the writing arm increases, writing moment will increase. Writing moment is given by delta into writing arm Gz. Therefore, if your Gz increases, your writing moment increases, and when your writing moment, what do you mean by writing moment? That is, if there is a moment causing it, for example, wind is acting, if the ship is like this initially, you have delta that is acting at the center of gravity, that is a weight acting downwards, and you have just exactly below that you have the center of buoyancy from where the buoyancy force acts upwards. So, these two forces are in one line and they are balancing each other. Since they are in one line, they do not produce a moment. So, it is exactly stable. Now, a wind is acting which causes the ship to heel, means it will one side is immersed and one side is coming out, and as a result of it B shifts because the volume inside has changed, more volume on this side, less volume. So, buoyancy has shifted here. Now, because of this, weight still acts vertically down at the G, the center of buoyancy, the buoyancy force acts up. This, there is a moment that is produced as a result of this difference in the positions, means it is not in one straight line now, G and B are not in one straight line, they are in, B is now here. So, G, the delta acts here, and B, this delta acts here. So, they are now separated by a distance. This moment causes it to rotate like this, getting it to coming back to its original position. So, if the wind moment caused it to turn like this, this moment will try to push it back to the original position. That is why it is called a righting moment. It is trying to right the ship, bring it back to the original position, okay, to remove the imposed moment, it is a righting moment. That is why that term righting moment comes, and that name righting arm. So, if you see that if your righting arm increases, Gz increases, that means your righting moment increases, as a result of which your tendency to come back increases. The moment that asking it to come back to its original shape, original position increases. Now, if you look at this figure, what do you see? Up when in the initial stage, let us consider this region. In the initial area part, first area, in this part you see that when your heel angle increases, means ship is initially like this, it started to heel and its heel angle keeps increasing. So, it is heeling, but what is happening when it keeps heeling, when the heeling angle increases, Gz keeps increasing. That is what this figure shows in this part of the curve. So, Gz keeps increasing means that moment keeps increasing, the righting moment keeps increasing. This is not the, there are two moments which we should know, they are known as heeling moment. That is why some people write in the paper some strange things like moment increases means which moment, that is there is a heeling moment and there is a righting moment. Heeling moment means the moment that is causing the ship to incline or increase the phi. So, heeling moment tries to increase the phi, it tries to heel the ship, it tries to increase your phi, whereas your righting moment is a moment that is caused due to the ship itself, it is not caused due to the wind. The righting moment is not due to the wind, that righting moment is a moment that tries to bring the ship back to its original position, it is due to the ship, it tends to decrease phi, it is actually trying to bring it back to the original position, upright position, that is your righting moment. So, one tries to increase phi whereas the other tries to decrease phi. So, that is your heeling moment and righting moment. So, righting arm is associated with the righting moment, not the heeling moment. Heeling moment is associated with the wind, or okay, two moments that mostly contribute to this are wind, then shifting of weights. Shifting of weights. So, you know that when a weight is shifted, the G will shift and as a result of it, it will try to heel, that is one. Then actually turning, you will see that when a ship is trying to turn, means like this, if ship is going in a straight line and then it has to go in a line like this, it has to turn like this. When it has to turn, some new forces act, centrifugal forces, and these centrifugal forces will cause the ship to heel, it will cause it to tilt. Now, so these are the three forces that cause the heeling moment. Now, for the time being, we are not interested in the heeling moment as such, let us forget that. This statical curve of stability is associated with the righting moment. So, this figure is actually showing your righting moment, and in some statical curves of stability, we also draw a heeling moment, which will come in the next chapter. We are not going to do that now. Right now, we are just drawing the righting curve. So, okay. So, once you know this heeling moment and righting moment, now we have this curve. So, let us go back to what I was saying. In the initial stage, in the first area region, in this region you see that as the heeling angle keeps increasing, so the wind is acting, wind is causing it to turn, as a result of which it keeps heeling, and as it keeps heeling, the phi keeps increasing. Okay. And as the phi keeps increasing, this shows that Gz will keep increasing. When Gz keeps increasing, the meaning is that the righting moment keeps increasing. Now, if this heeling moment is constant, if this keeps going, time will come when the righting moment will become equal to the heeling moment, okay, then it will stop. And then suppose that the heeling moment stops, means the wind stops suddenly, then this will come back to its original shape. So, this is what happens. Now, but what it shows here is that suppose it keeps going heeling, and once it crosses this region, what does this show? Here it shows that once it crosses this region into the second area region, as your heeling keeps increasing, your righting moment keeps decreasing. That means the righting moment keeps decreasing, this tendency keeps increasing. What will happen? The ship will capsize. That is the tendency. Its tendency to come back decreases, its tendency to go in this direction keeps increasing. So, it has a tendency to capsize in this region. So, this region is associated mostly with capsizing, and this region is associated with coming back to its original shape or stable. So, this region is stable and this region has a tendency to capsize, two regions of the statical stability curve. Okay. Now, and this angle, at this angle you see that Gz is 0, there is nothing causing the ship to come back, that is known as the angle of vanishing stability. Okay, now some more things are there in this. Yeah. Which one in the second region? It shows, no, the figure itself shows that as your healing angle is increasing, you see this, as your healing angle is increasing means as I keep going in this direction, healing angle keeps increasing, Gz keeps decreasing.
In that figure, in the cross-sectional figure.
Which cross-sectional figure?
The mid-ship section, we have drawn G is acting and Y force is acting. So then how Gz is decreasing?
In that geometrically?
Yes, sir.
Geometrically I have to draw and see then probably. Gz, if you tilt it too much, actually I have to draw that and see, I will tell you in the next class, okay. But that is a good question, yeah. So, you will see that when you, it is actually a geometry, it's you just have to extend this figure for a, when the, we have only drawn very small heel angles. This is a case when the heel angle, so the ship is almost like this, it becomes slightly different from the normal case, right. When you saying that the heel angle is crossed this region, it means that the heel angle has crossed very large values. It's this, okay, I haven't mentioned the values here. This is of course 0 degrees, okay, and this is, it varies for ships actually, because means it depends upon the shape of the ship where the Gz becomes 0, that angle of vanishing stability, it is not always fixed for all different kinds of ships. Gz, that value will depend upon the breadth of the ship, the draft, things like that. It depends on all those factors, and in general you will see that it is around around 70 to 80 degrees, okay. Roughly around 80 degrees you get, it is almost, that means it is almost capsized. 90 degrees means ship is like this now, a ship that should be like this is like this now. So, it is like that, somewhere around there it will completely, so that means once you reach 80 there is no chance of saving the ship, it is gone after that. So, and it is not always 80, because I have seen small some smaller vessels which fully capsized at 50, 55 and all that. So, it varies, but in general it, that is in some of the figures, I mean in some of the curves drawn here it is around 80 to 90. Okay, now okay, now okay, now let us call this angle alpha. Therefore, tan alpha, that alpha is the angle that is this line, it is not, it does not clear from the figure, but it is actually a tangent to this curve at phi equal to 0, okay. So, this line, the line is a tangent to, it is called the Gz curve. I mean just know that it is called a what do you mean by Gz curve? This is the Gz curve. Gz curve, statical stability curve, two names for it. So, tangent to the Gz curve at phi equal to 0. Okay. Now tan alpha at phi equal to 0 is given by right tan theta is equal to dy by dz dy by dx. Okay. So, dy is d of gz divided by x is phi. So, tan theta is d gz by d phi at phi equal to 0, that is what we are interested in, at phi equal to 0. Now, I am going to expand this. Now, I will do one thing, I will write that gz, we have already derived this formula. Okay. This I have derived. So, I will use this. Therefore, tan alpha at phi equal to 0 becomes integral of d of gm sin phi by d phi at phi equal to 0. Then it becomes, now I will just expand by parts. So, sin phi into or d gm by d phi into sin phi at phi equal to 0. Now, this is a constant, we will take outside, plus gm d by d phi of sin phi at phi equal to 0. Now, this is equal to, this is 0, plus gm cos phi at phi equal to 0, cos 0 is 1. So, this is equal to gm. Okay. Now, what are we seeing, what does this mean? That is, what it says is that tan alpha at this point is equal to gm, that is what we have derived from our series of reasonings. So, now what you can do is, let us take a region of, now you have here phi we are going to represent in radians. Okay. Suppose we represent, the previous figure they have drawn in degrees, but it does not matter, you change it into radians. I am sure you know this, pi radians is equal to 180 degrees. So, with that conversion you change this into radians, and at a region of about 1 radian, what is the symbol for a radian? 1 radian. Now, at the angle of 1 radian you draw a vertical, okay, and let that vertical hit the tangent somewhere, it is hitting here. So, what do we have here? We have drawn a tangent at phi equal to 0, it goes straight, it is a straight line like this, it goes straight, and at a radian of 1, at a angle of 1 radian I am drawing a vertical. Okay. So, what does tan alpha represent here in this figure? Tan alpha is equal to this distance, that is the y distance, this distance divided by this, and that distance we have said to be 1 radian. So, it is 1. Therefore, this tan alpha is equal to gm. So, this height is equal to gm. This is the statement for it, that is, if you draw the gz curve, first you draw the gz curve, that is, you have drawn this curve, you draw a tangent at phi equal to 0 here. For this curve you are drawing a tangent at phi equal to 0. If you measure a distance of 1 radian here and you draw a vertical there, these two lines will meet, this line and this line will meet at a point, this height will be equal to gm. Okay. So, this is just some reasonings, I mean just some mathematics you are doing around, but this is a very important concept. This method of doing it is very important, and this is a way of, so in this figure the most important thing probably is the shape of this curve going up and down, and the meaning of it, that is that gz increases in one region with an increase in phi, in the other region gz decreases with an increase in phi. So, this region is classified as stable and this region has a tendency to capsize, that is the first part of the statical stability curve. And the next one, number 2, the second part is this thing. If you draw a tangent at phi equal to 0 to the statical stability curve, this tangent, let that be one line. If you draw another line at a radian of 1, at a degree of, at a phi heel angle of 1 radians, at a heel angle of 1 radians, if I draw a vertical, they will intersect at one point, this point B, this distance will be equal to GM. Okay, that is the second concept. So, these two things you have to remember if you are going to be in the field of naval architecture, you will have to remember it throughout your career. Okay. So, this is that important a concept. Yes.
The capsizing part is GM greater than 0 or less than 0?
GM.
The capsizing
well, is it your question probably is that exactly at after this point does GM become 0, right? GM becomes less than 0.
If you're saying it's unstable, I mean,
Actually, in this case the thing is that the writing moment is always less than the healing moment. Okay, it depends upon the healing moment and the writing moment. Now, this is a relative, this figure actually shows a relative, this capsizing that I said is because of the relative activity of healing and writing. Okay. GM less than 0 really implies that it does not imply any healing. Even if there is no healing or not, the ship whatever you put there it will generally capsize. That is the condition for the GM less than 0 instability. So, this is not probably GM less than 0, GM will be greater than 0, it is slightly stable, but if the healing continues to act it becomes unstable at the end by the time it becomes. Okay, that is the meaning. Now, GM less than 0 implies that whether there is healing or not it does not matter, it is unstable, it just capsizes. That is it's if you put it there it will go down, it will capsize. This does not say that it will have GM greater than 0. So, it is not fully going to capsize, but it is not stable. If the healing continues to act, healing will be more than the writing, and as a result after one point it will capsize. In that point probably GM less than 0 will come. I have not really checked that yet.
So at the second point where the graph
touches angle of vanishing stability, you are saying there it is possible that GM becomes less than 0. I have to check that, because if I have to check that GZ is 0,
M and G are at the same point.
yes, M and G are at the same point, you are right, that is the condition, that is right. So, when GZ becomes 0, yes, that is mathematically stating it, when GZ becomes 0 as it goes down and comes down, when it reaches here GZ is 0, and when GZ is 0 GM sin phi is 0. Therefore, it implies that GM is 0 because sin phi is not 0. So, GM is 0, and if GM is 0 that means G and M have come to the same point. From that point below the, so this region actually you cannot, GM will be greater than 0, but as I said healing will be greater than writing, and as if there is healing acting it has a tendency to capsize. But if there is no healing acting, let us suppose that it reached this stage and the healing moment stopped, that means the wind stopped, it is like this and suddenly the wind stopped, then it will come back to the original position, otherwise it will capsize. So, in that sense it is unstable and stable, but in this case it does not matter, the healing moment will be greater, it will try to come back only. Healing means that writing moment is greater than healing moment, so this will be more, it will tend to come back like that. Okay. So, this is what it is saying. In the curve of statical stability at a heel angle of 1 radians, draw a vertical and measure on it that is the second another way of doing it, that is draw on it a vertical, means if you take this 1 radian and if you draw on it a vertical and measure GM, means measure GM on it, and then you connect it with the origin, that line will be a tangent to this curve. I mean that is the other way of round way of going about it. Okay. Now, I will do some other things in this. The same thing is done slightly different in this book. Some points you will get new points. Now, same things, just some little bit of extension. Actually, here they are giving some, we have done a couple of cases. Now, if there are slight deviations from it, for instance, this figure initially like this, heels like this. So, initially here let us say this is G and this is B, B0 goes to B1, this is m. Now, if you can, this is just a extension of this. Now, suppose this is at a particular heel, that is it is initially upright, it has healed from this position and it has healed to some new angle phi. Now, suppose it heals further based on this phi, it heals further. Okay, it is going to heal further. What will happen? B1, this position will now go to B, just heal further. Okay, that is, it has healed further, it will go to B2. Okay, it will go to a new point B2, and from B2 if you draw a vertical, this is the new and if you draw a vertical, now you see this is something that we haven't discussed, but it is how it comes. If it heals further to B2, how will you get the new position of metacenter? You see that the position of metacenter has shifted. This is just a very in general, you will see when you are doing this book, Biren's book, every point at very important points he would have sent, we make the assumption that the metacenter does not shift. Now, you will wonder how can the metacenter shift, when can it shift, like what is the condition under which it can shift. That you can see here in this figure. You can see this figure says that, let us suppose it is, in general we talk about small angles of heel. Okay, that is what we have done so far in all the derivations. We have said that angle of heel is less than probably 10 degrees. Okay, we said that. So, in that case this position of B1 is not very far from B0. Similarly, the position of B2, the final angle, if it shifts further, since the phi is always less than, let us say 10 degrees, this B2 is not very far from B0, and we say that this m does not shift from this point. But in reality, let us assume that it is healing through larger angles. In this case, as this figure shows, it is initially B0, it went to B1 and to B2. The way really to get the new position of metacenter is, from this B2 you draw a vertical to this new position, you draw a perpendicular to this new water line. This is W2 L2, this is W1 L1, and this is W0 L0. So, to this W2 L2 you draw a vertical. This is actually does not show here, but it is actually perpendicular. Okay, it is perpendicular to that, and where it hits the perpendicular B1 M, it is not the perpendicular to this, it is actually should the perpendicular to this. When it hits that, that is the new position of metacenter, because it healed from this position, it healed here. Now, it is staying like this, from here it is healing like this further. Therefore, this new buoyancy should be related to the buoyancy just before that, B1. As a result of this, this M2 is the position of your new metacenter. So, M2 is not exactly M. So, such a case can arise, you just know that, that is all. I do not think you will use it anywhere, but this is how the metacenter can be different. If the what?
So, shouldn't the metacenter, new metacenter be below the old metacenter, because if we increase the heel,
Why should it be below? It is tilted? No, it will be more. No, let us see. Just think of it like this. It is like when it is here, it tilted like this. Metacenter went up. It's tilting like this. Metacenter will go up only.
it will become more stable.
It depends. We can't say.
Okay, let me see. It's
Initially it may increase, and after attaining some height it will increase.
what?
Because when we go on healing it,
Yeah.
first we see in this GZ curve,
Yeah.
for stability
Is increasing. Yeah, good point. Yeah, that is answer. Actually, it's correct. GM increases, because as you see that saw that GZ curve in the initial part, GZ is increasing. That is a good point. You are thinking very fast. Okay, that is in this GZ curve. You see this in this part, GZ is increasing. So, this is the region we are talking about. I mean, the figure that I have drawn here is this region. So, GZ is increasing means GM sin phi is GZ, therefore, GM is increasing. That is correct. The stability will actually increase in this region, but when it crosses the region, it will be different. to really see that you will have to draw it and see. I think you will have to draw all the in the very extreme cases and see. It's going to be a little complicated. I'm not sure how the M curve will, how the M will shift such that the when it crosses this region, I'm saying. Till then it's okay, it will be just like this.
Finally, we know that GM becomes 0 at when
We know that that means GM has to GM means this vertical distance, it might be here, M might be here, okay, it might not be, but this distance might be 0, means the vertical distance between G and M becomes 0. So what is happening here is GM is shifting here, M is shifting here, M is initially here, then it shifts here, shifting here. What it says is that it should keep going like this. It will reach a highest point, and then after that it will keep going down, and it will keep going down, and it will come down here somewhere. So at this point GM will become 0. The vertical distance, a metacenter becomes here and G becomes here. That means the ship by that time is angle of vanishing stability has reached. That means as far as we cannot say about the phi, we cannot say, I think right now. Let me see. Phi can be anything. Yeah, it's roughly, that's what we have shown. It can be roughly around 80 to 90 degrees. That means the ship, which is initially like this, is almost like this now. Almost 90 degrees, but almost 90 degree one perpendicular turn has come, and at that point metacenter is at the same vertical height as G. So both of them are at the same vertical height. So this curve metacenter is really shifting like this. So if you draw a metacentric height curve, I mean that is called a M curve. It goes like this. Initially it's here. Let's say this is the initial center line. When it is in the vertical, in the vertical case, it's like this. Then if this metacenter M, it goes like this, and somewhere it reaches a maximum, and then it starts coming down, and it will reach here. At this point, at this curve, the ship is almost like this. Ship is almost like this. So it's almost 90 degrees now. Okay. So these are some. If you remember, we did once a problem that told you how to draw the B curve. So these are actually two important curves. So this you have to remember how that B curve comes. We have already seen this curve is called the B curve. Okay, this curve is this, how the B moves is known as a B curve. Now this M movement is known as the M curve. B curve, will it always go up? I think it will always go up because the ship is always turning like this. That means the volume here is always increasing. So therefore B has to keep going up. I think so. B will always keep going up, but the M will go up and come down. Now to really see that, as you are trying to say in a geometrical form, we will have to actually in this book, one of the problems which I didn't do is a computer simulation. They have asked you to draw the M curve. So you have a way of getting the M equation, means the position of the metacenter. M curve means you probably will not be able to get an expression for the horizontal distance, means where is M curve? This is the M curve. You might not be able to get this, but you will always be able to get this, which is GM, means you get a value for GM as a function of phi. You will have to keep doing this. In fact, this might be the best way to get your GZ curve. You are saying how does this GZ curve go up and come down? Best way is to plot GM as a function of phi. Now you know that you know how to find GM as a function of phi, like this. What is it? BM kg plus GM, no, kg plus GM minus. Actually, you have to see, if you remember that, you have to get that expression for BM. Okay, using BM, you know that BM is, you know BM from I by del. So from BM you should be able to get, and suppose you know the initial kg, so you know kg and BM. Okay, I'll stop here, but quickly I'll say this: kg and BM, once you have, actually you should know that when the ship is heeling, your BM keeps changing. Do you know that? Is it obvious why the BM keeps changing? Because the I keeps changing. I is no longer, the water plane area is no longer the same. Initially it was this water plane area, then it became a water plane area like this, then it became a water plane area like this. It becomes longer and longer. So I keeps changing, so BM keeps changing. As a result of this BM's change, GM will keep changing. Okay, you get BM from these two, you get that expression. So, GM keeps changing, and once you get the change of GM, GM sin phi will give you the change in GZ. Actually, that will be the way to solve your problem. What you said, you to get the GZ curve, you'll have to follow this method. I think this is the only possible way of solving this problem. Okay. So, that will give you GZ as a function of phi, because otherwise there is no straightaway way of getting GZ. How will you plot GZ? You cannot get it, but you can get GM. You can get GM from BM, and BM you can get as a function of phi, because I you can get as a function of phi, like that. You have to connect like that. Okay, I will stop here. Thank you.